All right, hi everyone, I'm Vinnie. I'm a production engineer at Meta. For the last couple of years, I've been working on image build tooling, and that's what I'm going to talk about today. Antler2 deterministic image builds with buck2. You'll note there's a 2 next to both of these. Clearly, we didn't get it right the first time, but I think we did a better job the second time. So, a few things I'm going to talk about. What do we want from image builds at Meta? What's buck2? Why is it useful and interesting? How we build, test, and package images. And how we wrangled some upstream tooling to behave a little bit more reproducibly. And the future open source work that we have planned. So starting off, what do we want out of image builds at Meta? The biggest thing is reproducibility. If we're going to release an image into production, we want to make sure that we can always rebuild it in an equivalent, if not exactly bitwise reproducible way from source control, such that we get the same image every time we use the same source control checkout. We also want image builds to be predictable. We have a lot of users that are all building images, and they should be able to understand what their image build is going to do without having to read a ton of man pages and without having a ton of implicit behavior that they have to be aware of. We want to make it easy to mix internal code and pre-built dependencies. Don't have to rewrite the world. Our users care about the code that they want to write, not necessarily all of its dependencies. So we want to be able to reuse pre-built things, usually RPMs, from internal or external repos. We have 2 main kinds of images we want to build with the same system. Full OS images for bare metal hosts and virtual machines, and lightweight containers with just a single service or maybe a couple binaries. We want our images to be testable because we all know if you don't test something, it breaks. Image builds should be just as easily testable as anything else that we produce. We want to integrate with the systems that we use internally. They should look just like any other deployable artifacts, just like a binary service that you built. So that brings us to buck2, which is the main system that we want to integrate with to enable image builds to work in a standardized way, just like everything else. So this is a talk about image builds, not generic buck builds, which could be a bunch of talks on its own. So just a very quick intro to buck2 and why it's interesting. It's what we use to build almost everything, with a few exceptions like big external projects like the kernel. It's a large monorepo build system for multi-language projects. It has a very rich dependency graph that you can query and use while you're building things. It has a lot of integration with different language test frameworks, so you get all your tests reported in a standardized way. It's easy to write new rules with this language called Starlark, which is basically just a small deterministic flavor of Python. And there's some really cool advanced features that aren't typically present in other build systems like this, like dynamic dependencies, where we can produce new dependencies that the user didn't necessarily declare. So quick touch on buck2. Now the interesting part is Antler2, which is our image builder. So with all of those things that we want, we came up with a few design goals for the API that we would provide users and how it works. Like I said before, all these features should be reproducible if you check out the same source rev, which implies that we can't arbitrarily use tools from the host unless their version is pinned in the repo somehow. All the features that are going into an image must be explicitly defined by the user, kind of principle of least surprise. If you didn't ask for it, you shouldn't get it. Any kind of file system dependencies, we do our best to validate before we even try to build an image so that we get fast feedback if any kind of preconditions aren't satisfied. Conflicting definitions should be also fast failures. Like if you try to install 2 different binaries to the same path, that's probably not what you want. We shouldn't allow it. And any kind of illogical setup of an image should also be a fast error. Like if you tried to create a user account in a container that doesn't have Etsy password or anything but like a single service binary. So we need an API to align with these goals and make it easier for users to declaratively define a file system. Some of the things that we need to be able to express in this API are inheritance between different images, a set of features to safely compose file system features where we can, like files, directories, files, symlinks, users, OS packages, and then sometimes you have to run arbitrary user commands. And we want to manage higher level aspects of OS distributions that we don't really want our users to care too much about. Like it's not safe to mix CentOS 8 and CentOS 9 RPMs in the same image, something that people try to do. So this might look a little weird if you're not familiar with Buck or Bazel or Blaze or Pants or any other Starlark build system, but this might be something like what we want our user API to look like. In this hypothetical, we have someone building a Rust binary, my service. Maybe that shells out to FFmpeg, and this user wants to build a container that deploys on the container fleet. And we don't really want them to have to care too much about where like FFmpeg is coming from. They should just be able to say, give me the RPM, and I'll shell out to it. So we can achieve most of the safety goals and reproducibility that I was talking about with a special file system aware dependency graph that we implemented in Antler2. And so the key components of this is every part of this image API fully declares all of the file system attributes and users and things like that it requires and that it produces, which means that we can topologically sort the graph so that we know that everything is satisfied, and we can have very simple build code because we know that everything has been done in the right order already. The graph lets us validate all those dependencies. Like I said, we want these things to be fast errors. So if you have something like a missing edge or two edges pointing to the same node, those are failures, conflicts. And then images can inherit the dependency graph from a previous image. So I'll give an example of that because it's not super clear from just reading the text. If we have a user that wants to create a new directory and install a file into it, they can write something like this. I'm installing the source file foo into a path /bar/baz, and I'm going to create that directory bar, assuming we're starting from an empty image. So in no particular order, these features get added to a dependency graph, which starts out empty. So we have these two features, ensure does exist and install. Now that we've put those into the graph, we can query them for the things that they provide. Sorry. So we see that the ensure does exists, or makedir if you prefer, provides this directory bar, and the install feature provides a file at /bar/baz. The reason the edges point to the feature will become more clear in a second. Then we query the dependencies, and we see that ensure does exists requires the root directory because it's the parent of bar. That always exists, so we can kind of ignore that. But we get a new dependency from install onto that bar directory, because we can't write the file until the parent directory exists. So if I rearrange this to match the topological sorting a little bit, and just include the nodes that are reachable from the features that the user wanted, we can see that we're going to sorry, I'll just go to the next slide. I'll rearrange it. It's easier. I'm just removing all the non-feature nodes and reversing the order a little bit, so we see what the image builder has to work with. So the topological sorting had install going towards the makedir, and now we just reverse it, and that's the order in which we're going to build our image. But it's also interesting to see what this looks like if you have something that's wrong, because good error messages are important. So it starts out the same kind of. I'm trying to install a file, but I don't create the directory that it's going into. So I add the install feature. It provides this path. And now I query it for its requirements, and I see it requires something that's a directory at /bar. And I colored it red here because that doesn't exist. So oops. Will fail before we even touch the file system and tell the user exactly what happened, that their install feature required this directory bar, and it didn't exist. Also, another interesting bug, or not bug, but incorrect image definition would be something that has a conflict. So if we add two install features that are trying to write, say, different binaries to the same path, that's something that's probably wrong. We could just choose the second one, but that would be confusing. So we do the same thing. Add the feature nodes. We see that they both provide this file at /bar, and that's wrong because we have two edges coming out of that same node. So again, we fail immediately before even touching the file system. So dep graph is all fine and good for nicely defined features that the user requests. But unfortunately, we live in a world with a lot of older tools that are not designed to operate in the context of trying to deterministically build an image, and we kind of have to shoehorn them in to fit. For example, at Meta, we build images with DNF and chef, random user command lines. So we have to find some way to make them all behave. So the easiest one that I'll start with is just arbitrary user commands, just like little shell scripts that users can write to do something that isn't supported by the declarative safe API. These are actually easier to wrangle than DNF and chef because they're all written by users that work at the same place, so we can tell them that they have limitations that they just have to accept. So the first thing is that we block network access. That's kind of the easiest thing to do and the biggest source of non-determinism and implicit dependencies. Another source of implicit dependencies, we block host file system access. The only thing that they get is the container image being built. They get run in a well-defined order, so we don't have any kind of race conditions or ordering issues that can introduce non-determinism. They run just after we install OS packages, which I'll get to in a second, and before all the nicely well-behaved features. But we don't generally sandbox these things. Like other than that, they can do whatever they want. Kind of by design, it's for things that we don't support in the declarative API, so they need to be able to do whatever they want to the image that we're building right now. So DNF is the most interesting tool that we work with upstream and getting it to behave deterministically. There's a few challenges because of how DNF is normally used. So like typically used on a running system that already has packages installed, either by a human manually, in the case of something like a laptop, or automation in data centers. It's almost always set up to point to some live, remote, mutable repository that's constantly changing, which is the point, right? Like you want to be able to install updates, get new packages that you didn't have before. Makes sense. DNF does dependency resolution for correctness, like satisfying all the dependencies that are there, not necessarily going to resolve the same set of installed packages in the same way every time if you install them in a different order. And RPM scriptlets, not really a DNF problem, but a problem with RPM, they can do whatever they want. They're just shell scripts, right? But despite all these challenges to determinism, we really need to be able to use DNF so that our image authors can use packages that are coming from upstream distros like CentOS or our internal repositories where teams publish code that they've tested already. So how do we kind of wrangle DNF to make it deterministic? We have to start with the repositories. If the repo changes, our image change. We can't have the repo changing underneath us. So we need a stable view of all the repositories. Yes? Okay. We need a stable view of all the repositories pinned to a specific source control. There are two obvious ways that we can accomplish this. The first one is just we can commit a URL to a repo that we can guarantee doesn't change. That works. Or we can fully represent the repos and all their dependencies in source control in our build system. We used to do the first one, but now we represent the entire repo in Buck. So starting from the ground up, we include a target for every single RPM that's available in every single repo. The repos collect all the packages that they contain. Repos are collected into a distribution, and then finally an image can depend on an entire distribution, and then 0 or more extra repositories. If we want to get like nightly builds of systemd for a specific image, we can do that, but obviously we don't want to do that everywhere. So I said that there were two obvious ways to snapshot repos. The first one seems a lot easier. We just make a copy of an entire repository and commit a single URL to the repo, to the source repo, sorry. But there's a key advantage to doing it like this, which is incremental updates. For example, when systemd 255 comes out, we can make a single atomic commit that takes us to systemd 255. And now if any images start failing tests or start breaking in prod, we can bisect exactly to that one change, which makes it a lot easier to figure out what's going wrong. So we have a representation of all the repositories in Buck. How do we make DNF work with it? Because we don't just have a URL that we can point it at. So we do this complicated little dance where we build repo data directories, like as if you were something you would host on an HTTP server for Yum. Antler will give that to the existing rootfs and all those repo data directories to DNF. We ask it to resolve whatever transaction is going to happen. And then we get to pass this back to Buck with these dynamic dependencies. So we ask buck2 to materialize all of the RPMs. So we know we only ever download an RPM a single time, and then we transcode it with RPM to extents, which is super cool. I don't have time to talk about that though. And then we invoke DNF again, where we've populated these repositories with only the RPMs that we're actually going to install. So at no point do we need DNF or Antler to be connected to a network at all. Finally, we reuse the same resolved transaction. So we don't ask DNF to resolve the transaction again. We just say explicitly install these packages, set the reasons correctly, and then we're done. So that gets us the packages installed and removed correctly. But DNF is still kind of has some footguns that we want to eliminate because we want to eliminate surprise. So for example, we never want to implicitly remove a package that a user explicitly asked for. For example, if you install pystemd, Python bindings to systemd, that requires LXML. If you then tried to remove LXML, DNF would normally happily remove pystemd for you as well, but we don't want that to happen because the user asked for pystemd, so we'll only let that happen if they request to remove both packages. And then also, new is not necessarily better. We have a lot of times where we want to either slowly roll out a package or pin it to an old version because there's a bug. So we built something similar to DNF version lock that's just easier to specify in images and equally importantly, easy to bypass. So testing images, we support a lot of things in repo like unit tests, booted container tests with systemd running as PID1, virtual machine tests, and images aren't super useful unless you're doing something with them. So we provide a number of ways that our users package up images, primarily Btrfs send streams, but also just raw loopback images, CPIO for initRDs, which we use a lot, tarballs, squash. We even support a simple RPM builder mechanism without having to go through like mock and RPM build and everything manually. Common question that I get is, because people are mostly building containers, is how does it compare to Docker build? Docker build, primarily a list of just shell commands, a few primitives. Similar caching model, but there's no safety like in the depth graph. You can just do whatever you want to clobber between layers with no warning. It's really hard to reproducibly build something with a Docker file because you're almost always running DNF update. And we have more test and deployment options. A few things that we want to do in the near future: support other distros and package managers like apt and pacman. We want to provide some public repo snapshots of like CentOS and Fedora instead of just the tools to create them. It would be nice to have something that you can use outside of Buck and more output formats. So thanks. Any questions? Yeah. I guess we need to wait for the...
Do you have a way to share image layers when you have containers with potentially large shared dependencies?
We have a way to build incremental send streams, but we don't really use that because the challenges of keeping the base image alive for the entire lifetime of the incremental is hard. But each individual layer is a Btrfs subvolume, so at build time we're not reusing all the same space. We're just snapshotting.
More questions? Yeah.
So in the example you just showed, like updating, thank you, updating systemd to like some random newer version, right? But most times it's not something like that, right? Let's say the newer systemd version needs a new GCC, but bumping GCC would basically break almost every downstream dependency. So how is that really handled?
Yeah, so we do have to bump, often we do have to bump multiple packages at once. So I use systemd as an example. The more common case is someone's bumping an internal package that nothing depends on and has no dependencies, because that's not really how we do things. And then that's what causes most of our breakage. But if you were updating systemd and it had a bunch of new dependencies, you would have to, like the tooling would update them all at once. Yeah, so you'd have an update commit that changes like 20 packages instead of like 1,000, right?
Yeah, so most of the times the problems with maintaining a tool chain is sometimes you update one, everything seems to work fine, and like a day or two later or after some commits, something starts breaking, and it's very hard to go bisect and figure out which update or which dependency update breaks something else.
Yeah.
Any more questions? No? Really? Oh, thank you.
Great. Thanks.